Hello, everybody. Continuing with our Henstitute video series on thermal radiation, I thought I would go with this idea. So let's say you have a wood-burning stove that's in your room, like pictured here. The stove has an emissivity of 0.9, and its surface area is 3.5 times or square meters. Sorry. The fire keeps the stove surface at a constant 198 degrees Celsius. So we have a constant temperature there. The room is at a constant temperature of 29 degrees Celsius. They want to know what is the net radiant heat generated by the stove in an hour. So if I kind of think of my equation, I know that Q is equal to emissivity, sigma, area, temperature to the fourth times time. So I have the time. My time is 1 hour, but that's going to be 3,600 seconds. So we'll just leave it like that. The other thing we have to do is change temperatures into Kelvin. So we're going to get into adding that 273 a lot. So I've got one temperature here of 198. I'm going to add 273 to that. And I'm just going to go with 273. I know that we actually have a 273 0.15. I'm also going to take this 29 degrees and add 273 to it to get 302 Kelvin. And we have this surface area, so we have that, and then emissivity. And then finally, our sigma is just our normal number. But the question is, what do I do when I have two different temperatures? What exactly is going on? And when they say the net radiant heat, what do they actually mean? Well, here's the idea. So the room is at 29 degrees Celsius, but the stove is at 198 degrees Celsius. So when I have some object, it's always going to radiate heat. So this stove is radiating heat out into the environment, out into the room. We know that because we're like, it's hot, so it's going to radiate that heat. But what we don't want to forget about is not only does something radiate heat, it also absorbs heat. And if you remember what I mentioned earlier, is when you're dealing with this temperature, this emissivity, it also indicates how much it absorbs. So there is also heat going in to the stove. So the stove is also absorbing heat from the environment. So when we actually deal with its radiant heat, we have to take both of them into account. So what we're actually looking at is the net heat is going to be the heat that is emitted minus the heat that is absorbed. Well, how do I figure out the heat emitted versus the heat absorbed? And it has to do with the temperatures. So in the case of the heat being emitted, it's going to be the temperature of the stove itself. But when we're talking about the amount that is being absorbed, we're actually going to take the temperature of the environment. So sometimes this will say heat absorbed. You're actually dealing with the environment. Can't spell environment here. And so that's what we're going to actually use. So when we solve this, the emissivity is the same. So it doesn't matter whether you're emitting or absorbing, the value is the same. Sigma is also the same, so that'll just get pulled out. The area, when you're emitting and you're absorbing, you have that same surface area. So the same surface area is going to happen. The time is going to be the same because we're doing this for an hour, but it's this temperature. So what we actually have is the temperature of the stove to the fourth power minus the temperature of the room. So it's going to be the temperature of your environment to the fourth power. So this is the thing that's going to be different, and this will give you the way to find your net heat that's actually being emitted or absorbed. So now I can plug in all my numbers, and we should be able to get it. I plug in my 0.9, multiply by 5.67 times 10 to the negative 8 times the area of this thing, which is 3.5, times the time, which is 3,600. So I have all these lovely numbers, 0.9, 5.67 times 10 to the negative 8. That's emissivity, or that's our Stefan-Boltzmann constant, 3.5 times 3600. Oops. Pen is not working real well here. Temperature of the stove, we're using the 471 to the fourth power minus the room, which is 302 to the fourth power. Take the difference, and that should find the amount of heat. And if it comes out to be a positive number, it means that we're emitting more than we are absorbing. If it was coming out with a negative number, it means we're absorbing more than we're emitting. But in this case, we know that that's going to definitely be emitting more because we are hotter. So we're going to take 471 to the fourth power minus our 302 to the fourth power. Trying to chunk all this stuff. Get a really big number here. Might be easier to write this in scientific notation. So I get 2 point, looks like I've got about 2 sig figs here, should be good. 2.6 times 10 to the 1, 2, 3, 4, 5, 6, 7. And this is heat, so it should be in joules. We have a nice little number. And that is how we use radiation when we have things that are differing in temperature, where we're absorbing and emitting. So we might actually be adding this to our equation sheet as well, or even this bottom little equation here to kind of take that into account. The last thing, since we're dealing with our Build a Better Thermos project, I thought I would point this out. When you have a thermos bottle, it's going to try to minimize heat transfer with all 3 of these methods. Conduction is the most obvious because you're going to put insulating materials, things with low thermal conductivities. Convection is also on there because you're going to stopper the top. You don't want any air flow. You don't want any fluid flow to actually have happening here. The third one is radiation. This one is kind of gets lost sometimes, but you'll notice sometimes on the inside of a thermos, you'll actually have some silvered material. And what that means is we're trying to get, if this is hot, then the environment, we don't want that heat to get out. We want that heat to hit this and actually get filtered back in, so to get reflected back in. If this is cold, we don't want the heat to come in, so we want the heat to hit this and get reflected out. So having that kind of shiny material is going to help us when we're actually dealing with that. So a lot of people in the past use some kind of aluminum foil to do that, but any kind of case where you can actually reflect some of that electromagnetic radiation is always good. And that sums up our second edition of thermal radiation. Hope you enjoyed.